Good morning. Can you hear me? If you can hear me, make comments on the chat box. And can you also see my share screen, the screen that I'm sharing? Good. So by 10 on the dot, we shall commence the class. For those students who may be unable to join this one because of the size, this can only take 300, and we have a class of more than 300. So you may pass this information to your colleagues if they are unable to join. They can go to YouTube and search for my name. My channel is Nehemiah A. Ikoba on YouTube. And you will see it also available there. So we shall be starting shortly. If you can't hear me, it may be as a result of network fluctuations. We just have to manage with it and hope that the network will be better. It's 10 o'clock already, so we can start the class right away. Our last class, we discussed about are you seeing the screen that I'm sharing? The slide that is being shown, can you see it? If you can see it, make your comments on the chat. Can you see what I'm writing on what I'm projecting to you? It's not loud enough. Are you hearing me clearly now? Can you hear me clearly? You have to, I hope you have joined with your audio. You join audio also. You see on the bottom left of your screen, of your Zoom screen, you see join audio. If you cannot hear me, that's the solution. But if it's quite low, This is, I will try to speak louder if that can help. So we shall be continuing with moment generating functions. Moment generating functions. Okay. Can you hear that? Moment generating functions. Any comments? Can you hear? So let's go to moment generating functions. In the last class, we introduced you to what is called the moment generating function. That is the expected value of an exponent e to power tx of any random variable, whether it is a discrete random variable or a continuous random variable. Now, if it is a discrete random variable, then the expectation given by the expected value of exponent of tx will take summation, while if it is a continuous random variable, the expected value will take the form of an integral. The moment generating function enables us to, as it were, generate moments of the probability distribution. It helps us to generate the moments of the distribution. The first moment is the mean. The second moment is the expected value of x squared. That is the second raw moment. While the nth raw moment is expected value of x to power n, which is given by Diggs. Now, expected value of x to power n, how do you obtain it using your moment generating function? You simply differentiate. You differentiate with respect to t n times. So if you want to find the second raw moment, that means you have to differentiate the mgf 2 times. With respect to t, you differentiate it 2 times with respect to t, and you will get the second raw moment. If you are to do the first raw moment, you differentiate it once and you will get the first raw moment. So essentially, that is what is being done in you can still not hear me very clearly. Okay, let me get a microphone and see whether it will work out. Hello, can you hear me? Can you hear me, please, if you can hear me? You can hear it faintly or you cannot hear at all. Can you hear at all or it's faint? It's still low. Can you hear me clearly? Let's continue like this. and we hope it will be better as we proceed further. Now, okay, loud and clear. Thank you, thank you. Somebody has said it is it's a bit loud now. So let us continue, please. So the MGF, you differentiate the MGF, the number of times to obtain whatever you desire, whatever moment you desire. For the nth one, you have to differentiate it n times with respect to t and evaluate it at t is equal to 0. When you put t is equal to 0 and evaluate, that will give you the raw moment. Now, the cumulant generating function is also there, which enables you to obtain cumulants. The first cumulant, if you take the natural logarithm of the MGF, you will obtain the cumulant generating function, which if you differentiate it once, it will give you the variance. If you evaluate the cumulant at with the cumulant as it is without differentiating, it will give you 0 if you have done it correctly. That is the nature of the cumulant generating function. It enables you to obtain central moments. So the first cumulant gives you 0. When you differentiate it the first time, it will give you the variance. So you can quickly obtain variance using the cumulant generating function. There are various properties of the MGF which we discussed last time out. That if x and y are independent, then the MGF of their sum is equal to the product of their individual MGF. This first property also extends to multiple sums. If you have k independent random variables, then it is possible for you to have the MGF of that k independent tying them together will give you the convolution also that. Thank you. Can you hear me now, please? Can you hear me now, please? Thank you. Thank you. Sorry for that. So I was just explaining the properties of the MGF. Of two independent random variables, their MGF is equal to the product of the individual MGF. So when you have two random variables, X and Y, and you have their product, you have their individual MGF, MXT and MYT. Then the MGF of that random variable X plus Y is equal to the product. You multiply both individual MGF together to get that MGF. And the explanation is, the proof or the how to go about it is specified in that property 1. Property 2 is saying that, or property 3 rather for emphasis, is saying that if you have two constants A and B, and you now have another variable that you define as equal to A plus BX, then the MGF of that new variable is equal to e to power at, that is the exponent of at, multiplied by the MGF of the random variable or ms of bt. ms of bt, that is, you use b to multiply t. Wherever you see t, you replace it by bt to get the MGF of that new random variable given by a plus bx. That is how to go about it. Then property 5, if you have a random variable that is now defined as x plus a all over b, then we can easily show that its own MGF is given by going through taking the expectation first. Thereafter, you now separate the constant from the variables. Because you have constant there, you can isolate it. That's why you have exponents to exponent at over b, which is now multiplied by msc over b. In essence, what this is saying is that if you have that kind of relationship, a random variable x with MGF mx of t and two constants a and b, and you now want to obtain the MGF of another variable which is equal to x plus a all over b, then you just have to have the exponent of at over b multiplying mx of t over b. That is for mxt. If you have mxt, wherever you see t, you replace it with t over b. Like in the case of exponential distribution that we talked about last week. If you are to obtain the MGF of x plus a all over b when x is exponentially distributed, it will be EAT over b multiplied by the mx t over b of exponential. Now the exponential distribution, the MGF is given by lambda over lambda t. So wherever you see t, you replace it with t over b. It will now be lambda over lambda minus t, which you can simplify further by the denominator resolving, and you will be able to have the corresponding MGF of that distribution. So that is that for the properties of the MGF. Let us now look at some examples. Previously, we looked at the case of the exponential distribution. We got the MGF last week, and we gave some we did some examples, or an example to obtain the mean, to obtain the variance, and so on. So continuing today, the first example that I want us to discuss is uh, the one relating to a binomial distribution. A binomial distribution. Now, a binomial distribution has only two parameters. The parameters of the binomial distribution are what and what. If you have that answer, please provide it for me. What are the parameters of a binomial distribution? Put it on the comments. I will see it right away. What are the parameters of a binomial distribution? Yes, the parameters of a binomial distribution are n and p. What does n represent and what does p represent? What does n represent and what does p represent? Make your comments on the chat. Yes, n is the size of the sample, the number of observations from the sample. Then p is not success, but probability of success. P is the probability of success. So N and P are just the parameters that you need for a binomial distribution. Of course, we know that a binomial distribution or a binomial experiment is relating to the number of successes. The random variable x is the number of successes in n trials of an experiment that only has two possible outcomes, success or failure. So n and p are the parameters of the binomial distribution. So the example, let us look at the example. It says that if you have, and it should show that the MGF of the binomial distribution is mx of t equal to q plus p exponent t, all in bracket, raised to power n. Then you will now use it to obtain the first two raw moments of the distribution. Now the solution. Of course, we know that p is the probability of success. Why q? What does q represent, please? Please explain what q represents on the chart. Quickly, so that I know that you know what you are doing. What does q represent? Q is the probability of failure. And p plus q is always equal to 1. So that is important. We will use it in our subsequent computations on this question. Now, the probability mass function of the binomial distribution with parameters n and p is given by p of x equal to n combination x. N combination x multiplied by p to power x and q to power n minus x. X takes values from 0 to n. You cannot take any other value apart from 0 to n. X is the probability, or rather, the number of successes in the n trials. So it is the random variable of interest, the number of successes when you are talking about a binomial distribution. The binomial distribution, as we know, is a discrete probability distribution. Hence, as I explained earlier, for us to obtain its moments, we have to use summation. We have to make use of summation to do our computation. So, summation or ms of p is expected value of this, which is the summation of tx, exponent of tx multiplied by the PMF, P of x, which is this. And you can now continue to resolve it and rearrange. Now you have x in the exponent and also x with p power. So you put them together. That is the strategy to enable you to really obtain the MGF of the binomial distribution. So when you have that, you put them together and put them inside the brackets to power x. This is just rearrangement. Then q to power n minus x. The next step is what is critical, and if you are able to grasp and understand this aspect, then you should be able to get this so quickly. We know that the binomial expansion, that if you have any two numbers, that two real numbers, then the power, when you have p plus q to power n, you are just having the binomial summation, binomial terms. For example, if n is equal to 5, please somebody should give me the coefficients of p plus q to power 5. What are the coefficients of p5, p4, p4q, p3q squared, p2q q, pq4, then q5? What will be the coefficient of p plus q to power 5? Please put that on the comments. What are the coefficients of p plus q to power 5 using binomial expansion? We did that last week, and I expect you to get that quickly. Or Pascal triangle, Pascal triangle. What are the components of p plus q to power 5? What are the coefficients? 1, 5, 10, 10, 5, 1. Correct. Correct, correct. So essentially, this is what you are making in p plus q to power n, because that is pq, p to power 5 multiplied by 1 plus 5 p to power 4 q plus 10 p to power 3 q squared, and so on. So it is a sum. That is why we have the summation sign here, beginning from when p is equal to 0. When x is equal to 0, up to when it is equal to the size of that thing. If it is 5 in our case, it will be 5 here. So that is what we make use of in trying to compute the, if we want to compute or to obtain the MGF of the binomial distribution. So you can see that it is a sum from 0 to n of a factorial, or combination rather, n combination x, px, and so on. For all real numbers p and q, that relationship holds. That is p plus q to power n. You can express it as a binomial expansion. You can using Pascal triangle, the principles of Pascal triangle. So with that, we can be able to look at what we have. You can see that what we have is p et to plus q to power n. That is essentially what is stated by our computation of mxt here. By our computation of mxt here on this line, you can see that this is equal, what we have here is the same as this right hand side of this. So we can see that this side here is equivalent to the left hand side, p et plus qn. So that is, we can now say, therefore, MST is equal to this left-hand side, PET plus QN, which you can rearrange by bringing the Q forward again to have Q plus PET to power N. So as required, we have been able to show that the MGF of the binomial distribution is given by Q plus P to power P exponent T, all raised to, all in bracket, raised to power N. Now the next thing is for us to obtain the moment, the raw moment. The first one, expected value of x, and the second one, expected value of x squared. So ms prime, when evaluated at t is equal to 0, will give you the expected value of x, which is for us to just differentiate mxt that we have obtained, q plus pet to power n, differentiate it once. What mathematical principle in differentiation do we use to differentiate a function of a function, sort of q plus pet all raised to please, sorry for the break. As you all know, it's as a result of the network. So uh, let us go back to what I was saying before the disruption. Please, can you hear me clearly, please? Can you hear me clearly? Let us continue with our notes, that the screen that we're sharing. Don't worry about having a screenshot of the note. I will give you that note. I will give it back. I will put it. Uh, I'll make it available to you. So just listen and follow what I'm doing. Look at the screen of whatever I'm doing. Uh, we will get it better. So let me continue with the sharing of my screen on the notes. Now, we were trying to obtain the first moment by differentiating q plus pet to power n. If you differentiate it once, you have this value, n multiplied by q plus pet to power n minus 1, then multiplied by pet. You first differentiate this function on its own as a power function, q to use it to be n multiplied by, or you reduce the power. That is the essence of function of a function. Differentiation is a function of a function. You are differentiating a function of a function. So you differentiate the main, the power function first, then what is inside you now differentiate later. That is why we have PET, because when you differentiate Q plus PET, it gives you PET. The only component that has T is this aspect. So when you evaluate it at T is equal to 0, certainly it will give you that. It will give you NP. It will give you NP. So that is the mean of the binomial distribution. The expected value of close the same procedure differentiates mxt two times with respect to t and evaluate it at t is equal to 0. So this is the first differentiation, m prime of xt. It gives you n multiplied by q plus pet to the power n minus 1 multiplied by pet. Now, you have, what principle will you use to differentiate mx prime t another time to have a proper solution? Please put that in your comments. What differentiation principle will you deploy to the ms prime t once more, so that you have ms prime prime of t? Yes, any comment? Yes, product rule. You make use of product rule in that regard. Product rule, use it to differentiate, and it is u the v the t plus v the u the t. Once you have differentiated it in that regard, you now evaluate it at t is equal to 0. And you obtain ms prime of 0 is equal to np 1 plus n minus 1 p, which is given there. So that is uh, the first two moments of the binomial distribution. Now, you can now, with that, you are able to obtain the variance of the binomial distribution. Using the principles, you have the variance of x is equal to expected value of x squared minus expected value of x all squared. So the variance will now be, what will be the variance of the binomial distribution using those computations? Having known that the mean is np, that is the value of x is np, and the expected value of x squared np into bracket 1 plus. So what will be the, yes, u. Take note, it is not capital N, it is not capital P, it is small n. There is a difference between capital N and small n. Capital N is the size of the population. Capital N is relating to the population, while small n is the size of the sample drawn from that population. P also is the probability of success from the population, while small p is the probability of success from the sample. So it is uh, that is the way to go about it to obtain the variance of the distribution, which is For example two, so exponent of lambda into lambda exponent of to e times the distribution. Now the solution goes thus. This Poisson distribution is given by lambda to x, lambda to power x over from 0
Can you hear me now? Hello?
can still hear. Discussion. We are looking at um, the Poisson distribution. It has the of this, and we have a situation.
Can you hear me? So discrete probability distribution, the Poisson is to obtain the MGF, you have to sum. So please bear with us. There are serious fluctuations on the network that is preventing us from having a smooth class. So are we having any echo from your hand? So Please, can you hear me now? Are we still having the echo? Are we still having any echo? Is there any echo again? Say no echo if there's no echo. Is there any echo? That means you are, and you can hear me clearly. Can you hear me clearly? Good. So let us continue what we are talking about. We are looking at the Poisson distribution. So I want to share the screen again. The Poisson, what we have been discussing thus far. So not to worry, I will give you the notes at the opportune time after the class. You have that notes as an additional understand the principles that we have to be able to do Can you hear me now? If you can hear, make a comment and say you can hear me clearly. Okay, thank you. So sorry for that break. It's as a result of network. It's as a result of the network. So um, let us continue what we were talking about. See from the screen. Hello, please. Can you hear me now, please? Thank you. Thank you. Sorry for those delays. Uh, so let us continue by I want to continue sharing that screen so that we'll be fast enough in explaining um, what we need. So the moment generating function is what we are talking about. And we are looking at the exponential, the Poisson distribution. So to take the expected value of the Poisson, you have to sum the exponent multiplied by the PMF, sum over the range of values of Poisson. What is the range of values of Poisson? Is between 0 and infinity. So that is what we have in the sum. And when we do all the necessary rearrangements, we have lambda et to power x over x factorial multiplied by e to my e minus lambda. So you can see that the sum of all the because the PMF is a probability distribution, the sum of all the values must be equal to 1. So once you have that is equal to 1, then you can now use that principle to resolve the MGF that we have at this stage. Because when you multiply both the numerator and denominator by e to power lambda et, and you rearrange it properly, that sum will resolve to something. You have this one outside, you have expected value of lambda et minus 1 outside, multiplying summation of from 0 to infinity of lambda et x to multiply by divide by the factorial and the sum, which will now finally resolve to exponent of lambda et minus 1 multiplied by 1. So you can see that this sum that I put arrow on is equal to 1. That's why you have 1 in the next after the equality sign again. On the right hand side, you have 1 there. So you can see that the MST, we have shown that the MST of the Poisson is equal to e to power lambda et minus 1. E to power et minus 1. That is what, that is the exponent, the MGF of a Poisson random variable. So if you have that, if you have a Poisson random variable, the MGF is given by what we have there. You will now differentiate it 2 times.
Unmute everybody. So now me be your Ogada. It's our Pulu. See, lecture I done this class. What's going on? Lecturer down. He said for me, say, oh, see. It don't happen, no. Positivos, yo. Lecturer, is that down. Yeah. Bóyá lẹ́sọ̀ gí sí sálọ́tà ẹ̀jẹ̀ omi sí gbogbo èèyàn ni wọ́n dá. Everybody on mute yo.
Answer for me. Let's make
Hello.
The class goes for today.
I want to do that. The man is back. In my kitchen too.
Just give up that. Go by class lónìí. Àwọn máa yà ọjọ́ mi. Àbí.
Àwọn dákun dátà mi fa.
Ẹ má kò dẹ́ wa mo lo dátà wa náà kí ló ṣẹlẹ̀ gan.
Èwo ni 15 hours of life, 15 hours of.
Ewedu keep quiet. Ewedu keep quiet.
Shut up. Anyone here?
I said the man is back. Guys, the man is back, I say.
Stop making noise. Mama, let's make out.
Anyone here?
Number one.
Let's make out.
Number one, man.
Is this class closed for today? Our Yemi Matthew, number one.
Number two, Mohammed Patiat.
Number two.
Mohammed Patiat.
Number two, Veda.
Number three, no visa.
Number three, my man.
Number three, no visa.
Number four, Usman.
Number five, Patiat.
It's okay. You people should stop the noise. You people should stop the noise. Lecturer,
The man should just give up. That I like this man strength too.
Oh, wake up, fam.
Oh yeah, sir. You can take over, sir. Sir, let's continue the class. You're not stopping.
Hello, Whoopi. Hello.
Yeah, it's okay. Let's stop all this thing. I'm the host again. Where are you on the class, Jimmy? What's going on now? What's the lecturer? Just calm down. You people should just calm down. The lecturer is coming back. The man will still come back. Oh, you were in the class. The lecturer about our class is already your class. Get it? I think the lecturer. Where is it? Okay, let me see.
Hello. Sorry for the break. So I will give you the notes right away, so that you can have it. Even if there are breaks, you can be going through it. They are quite explanatory, in addition to what we have given earlier. So I will do that right away now. So the Poisson distribution, as we have said, it has a mean of lambda and a variance of lambda also. So the mean and the variance of the Poisson distribution is the same value, lambda. So, and that is, we have explained how to go about getting it. And all other examples and the exercises in the notes, please, in the earlier note that I've sent to you, please take note of them and make use of them to do your own practice. By next week, hopefully, we shall be having an online quiz, really. An online quiz that you will be given a short amount of time to do certain computations in relation to what we have done so far. So I need you to practice as many as possible and ensure that master the principles that we have explained thus far. The mean and the variance of the Poisson is lambda. The expected value of x squared for the Poisson is lambda squared plus lambda. The cumulant generating function, that is the log of E of mxt. Okay, you have exam. Okay, the upper week then. The upper week, let us leave that out. We shall do the online quiz after the exams. We shall do the online quiz after the exam. The cumulant generating function of the Poisson, k of 0 is equal to 0. That is the first the cumulant without differentiate once. It gives you the variance and it's equal to lambda when you do that as well. Take the log of mxt for Poisson and differentiate it once and evaluate at t is equal to 0. It will give you the lambda, which is equal to the variance of the distribution. Now, the third example that we should also look at is in relation to the uniform distribution. The uniform distribution. Now, the uniform distribution, let's see whether I share that again. Can you see the screen? So the screen that I'm the third example, that you should find the MGF of the on the interval, closed interval A, comma B, closed interval A, comma B. You then have the variance of the uniform distribution.
This one don't tire me. The man has still left the class again. Right?
the PDF of the uniform distribution in the interval A, comma B is just 1 all over B minus A.
I do not ask anything. No, I don't know how I'm becoming your own too. No. No.
So are we seeing the screen now on uniform distribution? That the PDF is 1 minus B, 1 A and B.
Now, finish this platform now. Oof. I wish you had the class now. There was all this one. Continue, Kenny. Between the man, the self, I don't understand. I need to talk to call. Thanks. Like my name. Thank you. So your network is not good at all, Jerry. You are just wasting everything. Somebody did not understand the class. Yeah, me see that me father, Jerry. This is some job. This is noise.
Okay, please, can you hear me right now? Please, if you can hear may make a comment. Okay. What we'll do is this. Our time is almost, we still have maybe up to 30 minutes. But within that time now, between now and 30 minutes, 12 noon. So I'll put out the notes on that site. You can go there and download it. And also take the attendance there as well. Take attendance in that place. I will make the comment on the chat so that you all will see it. Take attendance on my website. Before noon. So you should go to that site and take the attendance there. I will also ensure that I put out the notes. I'll put it out there so that you can also download it and have a look at it. While we prepare for the test, which will be the upper week, not next week. The upper week will have that. So I think this at this point we can now end the meeting. We hope it will be better tomorrow when we have the next meeting from 4 p.m. So have a nice day.
I think we have end the class. Let me end the class. You should be refreshing the page. You will drop the attendance at the note. I will end the class now. Refresh the page. You drop the attendance and the note.
Ubeda, please drop the link for the man's website, please. Ubeda.
I've dropped the link now. Yes.
Where?
Okay, let me drop
Okay, I've seen it.
Wosi is no
Okay,
longer
just refresh the page
accepting
and
response.
No, you have not dropped the link for today. We will soon drop it. That's what it said the first time you're trying to do it. Maybe in the next 5 minutes, you can try it again. Or 2 minutes, I'll turn the class now. Bye.